All right. Well, we will go ahead and get started here. We are at 1:02. So with that, I would like to say once again, thank you all for joining us today for this American Makes TRX webinar. We're going to have Adva Cera presenting today. We have a couple folks from the team there that are going to share as we go through their presentation. To start things off, we're going to have Mr. Hugh Roberts, who is the president of Adva Cera, present. Hugh has been a former medical device professional for the past 25 years. He has executive commercialization and sales experience and is absolutely no stranger to bringing disruptive technologies to market. My apologies, everybody. Ceramic additive manufacturing has been no different. Hugh is a strong leader who creates opportunities by keeping a critical eye on the market, developing rapport with stakeholders, and mentoring his team to work through challenges in the ever-changing landscape of technology. With that, I'm going to hand it over to Hugh to kick things off and get the ball rolling. So Hugh, take it away.
Thank you, Zane, and thanks very much to America Makes for giving us this platform, this opportunity. Good morning, good afternoon to however it may be for each of you. Good evening to one of our members who's actually over in Munich, Germany presently. But thanks for joining us on our infomercial today. Adriana, can we get the slides up, or are they up?
Not seeing anything.
There we go. Perfect. There's our infomercial, printing the right parts, application-driven design for ceramic additive manufacturing. Next slide, please. So just a brief bit about Adva Cera. Some of you may have known us as Synaptic Technologies, our former name. We changed that name in November of 25. We moved forward after some things we'll talk about with the divestiture part of the company. But we are currently located in Broomfield. We've got about a 7,000-foot facility in which we have 10 full-time employees. We have 8 printers, and we have 10 furnaces of the debind and center variety. So we are a small but mighty team. Our mission is to lead the future of advanced manufacturing, to create complex and functional technical ceramic designs that can turn ideas into reality, and we really are seeing that happen. And our vision is to be the preeminent domestic producer of advanced ceramics that solve custom critical applications in the most demanding environments, which we're also doing. So it's been very interesting and exciting. Next slide, please. A bit of just the company timeline. The company was founded by me and by my co-founder, Dr. Brian Shear, in November of 22. We both had kind of come along this journey because of our interest in silicon nitride as a biomedical implant. We saw the benefits of it being able to outperform titanium or polymer implants, and was just a better choice for humans. But we also saw the limitations of traditional manufacturing of ceramics and how that really constrained the ability to develop and grow this material. When we got connected with folks primarily at Lithos to begin with and understood the true capacity of printing ceramics, it really was a game changer for what we thought the technology and what we thought our mission would be. As we began this journey, and again, as Zane said, but my background is medical device, my co-founder is an orthopedic surgeon. This was really going to be kind of the leading beacon for the company. But we quickly realized as we were starting down the path that there was really no company serving as a service provider, service bureau, if you will, for technical ceramics that were additively manufactured in any vertical, at least from a domestic perspective, and really not very many in the world as well. I think there's probably 5 companies that are very focused on printing additive ceramics. So we quickly pivoted and widened our scope and began looking at some of these other verticals that really had, much greater total addressable markets than the surgical market we were looking at. And, we began to really open this up and look at many different verticals for selling our parts. Along the way, we got some help from a great manufacturer in Elementum 3D. Many of you probably are familiar with them. They've been an America Makes member for a very long time. They actually brought us in and allowed us to bunk in with them on their campus for a couple of years as we started this process. We quickly began to take hold and grow and need more space. So in August of 24, we moved from out of their, basement, if you will, so to speak, and then moved into a new facility with about twice the size here where we are today in Broomfield, Colorado. I said earlier, we started this with surgical products in mind, and then began really to focus on other verticals that just were greater opportunities for us. And we realized that the surgical side of this, which was going to be manufacturing and commercial side of the company, was just taking too many of the resources, too much of the mind share, too much of the time. So beginning in early 25, we started looking at opportunities to divest ourselves of the surgical component of the company. And we did that in July of 25. We sold Synaptic Surgical and the Synaptic brand name to Syntex Technologies. Syntex is a traditional ceramic manufacturer and working very long time with silicon nitride in biomedical implants. And in fact, Syntex just did put out one of our initial products, a foot wedge that was first implanted in a human last week. So we're very excited to see what they do with this. And as a stakeholder in Syntex, we are their biggest cheerleaders and their biggest fans, and think they're going to do great with those surgical products. Off of that, we had an opportunity or a need really to change the name of the company, and felt that Synaptic, focused on silicon nitride on our original concept, was just too limiting, and it didn't really appropriately tell the story of who the company had become and where we were and the multitude of ceramics that we're currently working with. And so I will, we wanted to move this on to show that all the ceramics we have now demonstrated mastery in, and we'll talk about that a little bit later when we get into the application section of the presentation. We took several months to kind of come up with different ideas for name concept, and actually we'd love to take credit internally, but it was an external source, our rebranding consultant, that came up with Adva Cera, short for advanced ceramics, which certainly is where we are and certainly is more indicative of the company we've become. Now, some of you, and myself too, initially looked at this name and said, gosh, that seems an awful lot like adversary. And to a degree, it is, because we are adversarial to the limitations of traditional ceramic manufacturing and are for expanding indications and breaking down those barriers and really moving ceramics into a unique space with unique capabilities that we'll talk about in this presentation as well. But so that's where we are today. We are Adva Cera. And we've been Adva Cera now since November, and we continue to move forward and pioneering, first moving as a leader in the ceramic AM marketplace. Next slide, please. One of the things that we've learned along the way is that it really takes a village to embrace this additive manufacturing stage a journey that we are embarking on. And to that point, we've found some very good industry association partners and research partners. We do participate with AMUG, and we did actually give a presentation, not this year at the meeting, but 2 years ago. It's great to be at AMUG and really get to interact with disciples of additive manufacturing and the true believers and the folks that are really pushing, the evolution of this manufacturing concept. We are just about done with our inaugural year with America Makes, again, thanks to a sponsorship from Elementum 3D to start our journey here. And America Makes has been a great opportunity for us to further engage with folks in this community. And, obviously they are always coming up with new ways to bring in additive manufacturing to the forefront. Our mission is to embrace the additive manufacturing and really convince them why ceramics needs to be a greater part of it. So that's what we continue to do. Interestingly, we also are involved with Colorado Space Business Roundtable here in Colorado. I'll be quite candid, going into this from a medical background, I had no idea the size and scope of the aerospace ecosystem in the state of Colorado. It's wide and it's significant. And it's been really great to engage with the CSBR group to be able to meet with these folks from all of the various aerospace companies that are here. I'd certainly heard of Lockheed and Ball, now BAE Systems, but there's a whole host of companies here. Ursa Major, Agile Space, folks that are doing really cool things. And so that has been an added bonus for us to really engage with those folks. Additionally, from a research standpoint, we're continuing to push the limits of what we can do with the material and advance and solve issues and unlock challenges and those sorts of things. And, two organizations I'd really like to highlight here is we've begun a great association with Colorado School of Mines. They are one of the three preeminent ceramic programs, academic programs in the country. And it's given us a great opportunity to collaborate with their experts and also serve as a pipeline. We actually have a co-op here from Mines this year and want to continue to work and do development with Mines and collaboration and push this forward. Additionally, we're working with NIST to help develop standards for additive manufacturing ceramics. In fact, we are currently embarking with both School of Mines and NIST on a CRADA cooperative research and development agreement to start establishing more rigorous standards for the material. Next slide, please. So really, what has been my experience with this company over the last several years, there are three basic challenges. There are many challenges, but there are three top of mind challenges that we really have faced and focused on since we began this company. And the first, quite simply, is just lack of awareness of the fact that advanced ceramic parts can be printed, which is something people say all the time to us. I didn't know you could print ceramic parts, but you can. And our solution, next slide, please, is it's just obviously an opportunity for us to provide customer education on the existence and the rapid growth of the technology, and especially focusing on target applications that solve problems for those customers where we can help them out. Next slide, please. Challenge 2. Subtractive designs are not optimized and are often not appropriate for additive processes. Please, please, please don't bring me your traditional ball bearing that you've been making traditionally for years and years. We're not going to help you by making that better because we can print it. That's not really where our talent lies. Our talents are really more specifically where you need parts that are lightweighted or made more lightweight. Structural complexity, near net shape manufacturing is something we can do quite well. Part consolidation, taking 2 or 3 components and turning it into one part, I think is a great opportunity for AM ceramics. Anything where high resolution or internal geometries are important. One of the great things about additive manufacturing of ceramics is we're not limited by tooling requirements. So if you need a ball bearing with some sort of heat channeling or heat dissipation, that's a part you probably want to bring to us, and we can do that and make you satisfied and happy with what we're producing. But at the end of the day, really what this requires is collaboration with our customers, and that's essential for helping to educate and optimize designing for additive manufacturing. And, that's been a great opportunity for us to really open the minds and eyes of a lot of the engineers and folks that we work with to see really how they can push the boundaries of the parts they're trying to make with additive manufacturing of ceramics. Next slide, please. All right. Yeah, this is obviously a challenge for us as well, that adoption of AM ceramics is slow due to customers' uncertainty of performance. When we started the company, we recognized that we were going to be ahead of the market, as first movers generally are. And I think that the market is beginning really to catch up with us, but I kind of liken this to when electric cars first came out. People really thought that was interesting and thought they were great and weren't ready to buy them. They were just not sure. They were, just had some hesitation. And so we think that that's kind of some of what we do here. We do a lot of prototyping, but getting people comfortable with moving on to production, that's starting to happen much more regularly now, but it was a process for us in the beginning. And I think that some of this is really going to be best solved by our investment in testing and other activities to determine the material performance and see how well they hold up in end use environments. And, we are certainly in that stage of the game today and kind of solving and building that trust issue for our customers. And as I talked about earlier with NIST and with Colorado School of Mines, we're really looking to kind of develop more standards for AM ceramics because there just aren't many today, and create property libraries that we can develop to control material properties and really put out more and more information about these parts and how they are best suited to solve challenges and work in the marketplace today, despite what vertical that may be aerospace, semicon, industrial, what have you. Okay, those are the 3 challenges that I really think are at top of mind. And this is the end of my part of the presentation. So next slide, I'm going to turn this over to Adriana Joyce. And Adriana is an esteemed colleague of mine, and she runs all of the R&D initiatives for the company, which, as you all might imagine, are significant and copious, and she does a fantastic job. So she's going to spend a little time talking about technical capabilities.
Thanks, Hugh.
You bet.
Yeah, want to jump into some of the technical capabilities that we have, as well as some of the design considerations that we look at when working with printing ceramics. So here at Adva Cera, we've got two types of DLP printers. The lithos printer, which we have 6 of, has a 102 by 64 millimeter build plate. And the Z range is 320 millimeters. So we can print pretty tall parts, although they're not huge in the XY. And that is the build plate size. But because we are printing a ceramic part out of a polymer ceramic suspension, the dimensions of the final part are a little bit smaller, closer to a business card off the lithos printers. The light source on the lithos comes up from underneath. So looking here on the screen, you can see the lights going up from underneath. That build plate moves up and down over top of the vent. On the other hand, the second type of printer that we have is the Broadway Ceram Pro. This one is still DLP, but the mechanism is a little bit different. So the light is coming down from the top. It reflects off a mirror, projects down onto the build plate. So the parts become more and more submerged into the vat, into the slurry during the printing process. Pros and cons to both methods, and we'll talk a little bit more about how each one impacts the printing process. But one of the interesting bits about the Broadways is because this projector is up on the top side of the printer rather than underneath of that, it has a little bit more mobility. So this gives some modularity to this printer. A single exposure is 66 by 41 millimeters, but because the projector can move, the build plate is modular. So it can go from that single tile exposure up to a 32 tile build plate, making the maximum build plate 264 by 328 millimeters. Quite a bit larger than the lithos, although you are then working around the effects of that moving light. Printing ceramics in general, we can achieve fantastic parts, highly complex with excellent tolerances and sufficient strength for a wide variety of applications. Either of these printers work for a variety of parts, although we pick and choose which part works best depending on the part itself. We can lightweight parts with internal lattices, create complex internal channels for cooling application, and vary that strength and porosity as the application requires. As you can see in the middle image, the shrinkage during thermal processing is pretty significant. It's also anisotropic, ranging from 19 to 44%, depending on the exact material, both the resin system and the ceramic that we're working with. Despite this, we can produce parts that meet the specifications required by demanding aerospace and semiconductor industries. For example, if we print B-size bending bars, so 3 by 4 by 45 vertically, don't post-process them at all. So the surface texture that comes off the printer and out of the furnace, we can get a Weibull modulus of 8.3 and a characteristic strength of 387 megapascals. This is the worst case scenario for strength testing because any of the surface defects are still there and the force is being applied parallel to the layers. So it tests the interface strength as much as the inherent ceramic strength. To meet those demanding specifications, though, and truly print the best parts, there are some design considerations we have to take into account. So I'll walk you through some of those. When we're designing parts for additive, it's really easy to come up with ways to design the best part. Sure, we could take a part that was made subtractively and print it and get decent success. But if we start from the beginning by taking into consideration the way that the printers work, we get a much better final part. So we can make all of these complex internal features, but depending on how they're designed, you get different impacts. So if we look at this part here on the screen, we've got a through channel, a blind channel, and then a U-shape channel. And each of those have abilities to be cleaned because of the aspect ratio, how long and skinny they are. The blind hole is the least cleanable because while you can blast solvent in there, it doesn't really rinse out. The U-shaped channel, it has that feature down on the end, but it's a lot easier to clean because we can flow the solvent all the way through. Another problem with a feature like this is that if this bottom face is on the build plate of, say, the lithos printers, we're creating bubbles because air getting trapped in those channels each time the print comes down, the face contacts the build plate and it lifts back up. We're also limited by wall thickness. The raw material that we're working with is a suspension. Ceramic particles are suspended in this photopolymerizable resin. So the ceramic component is 40 to 60% of the green part, which means that we are burning off a large concentration of organic material. As that decomposes, the organic has to leave the part, and we want that to happen without damaging the part. That limits our wall thickness. Depending on the resin system and the ceramic percentage, the maximum wall thickness in the sintered state can be as little as 4 millimeters or as large as 10, but it's slurry and design dependent. So that's something that we like to work with customers from the beginning to address. Another design consideration is corners and angled features. The print resolution that we're working with is between 31 and 40 micron pixels. This is just a limitation of the printers themselves. That's the DLP set that we're working with. But another factor is that sharp corners are a stress concentration point. Factor for any gritty material like ceramics, but especially with the layer-wise buildup of the part during the printing process, if that layer transition and that layer interface aligns with a sharp corner, the stress is extra concentrated and it can cause delamination. But all of those challenges don't mean that we can't print great parts that include those features. What we like to do is include drain holes on closed features. So on that blind hole, we would put a smaller than the main drain hole so that we could flow the slurry through, clean it out really well. For the wall thickness, if we can make the wall thickness as consistent across the part as possible, so no very thin sections connected to a very thin section, our burn off during the polymer decomposition is a lot more consistent, which makes it less likely for stress to build up in any particular portion of the part. We can also fillet the corners and angles as much as possible. So the smoother and rounder features that we can make, the less stress concentration we get, and the better the final part comes out. That max wall thickness is material dependent because it depends on the resin system and the ceramic loading content. So that one we have to work through on a part dependent basis, but it's very easy to talk through that and make adjustments to parts if we know what the critical features are at the beginning before we ever start printing the part. Another aspect to consider is the fact that we're taking a native shape, so something with smooth curves, round features, and we're voxelating it. Think of it like making a sphere out of Legos. You know it's supposed to be a sphere, but depending on how big it is, it may look a lot more like a cube because your limiting factor is the size of those Lego bricks. The pixels on the lithos printers are 40 micron, and on the Prodways are 31. That means the minimum feature and tolerances have to account for the way the slice of an image is going to approximate a smooth curve by those tiny squares. The pixels on the printer take a 400 micron circle and approximate it like this. We've got some pretty harsh stepping and some very square aspects to what should be a circle. A straight line, a straight edge that is not aligned with the pixel grid becomes very stepped, and you get a stair step effect that looks like the printed part shown in figure B along the bottom. Radii that are approximated by very few pixel steps, like this one shown in B on the right side of the image, it doesn't approximate the size of the feature very well because we're using pixels that are larger than the change we need to make to our feature. But we've got a couple tools that we can use to work around these limitations of the technology. So if we know that we have critical features, such as the straight edge needs to be straight and smooth, we can align that to the pixel grid. So that one becomes smooth, and then less critical features can suffer that stepping effect. We can also size features if we're designing the part from the beginning to multiples of the pixels. Taking into account the scaling that we have to do for the shrinkage during debinding, we can make features pixel sizes and avoid that dimensional drift that occurs when a repeated feature or a repeated part doesn't stay constantly aligned with the pixel grid. There's also anti-aliasing. It's well established in other additive manufacturing processes, and that adjusts the intensity of individual pixels, giving us a grayscale effect, which lets us make this 7-inch radius curved feature much closer. So nominal is 7.1. Using the binary control, we achieved about 5.9 inches. But with anti-aliasing, we can get much closer to with a 7.5-inch radius on the final part. The same pixels that are approximating the native shape are projecting light up into the slurry. Fortunately, the light follows the laws of physics and doesn't stay contained in a perfect little square column, convenient as that would be. As the light travels up into the slurry from either direction, above or below, whichever way the projector is going, it encounters the ceramic particles that are suspended in the photopolymer resin. Those particles absorb and scatter the light, and the scattered light encounters photoinitiators outside of that desired curing zone. This causes overpolymerization and increases the dimension of our part outside of the design value. This effect is material, so the slurry that we're working with, intensity, amount of light coming up, and feature dependent. Looking at these images along the bottom, you can see that for a point, narrow versus wide, and internal versus external, we get a pretty dramatically different amount of overpolymerization, or overcure, depending on the terminology you want to use. And that's because depending on that cross-section, the total amount of light density around the point of that corner is different. So on the internal angles, we've got more light coming in from both sides, increasing the total amount of scatter and therefore the amount of overpolymerization. But again, with the knowledge that we have around this technology, we've got several ways to account for this. We can modify the exposure time and the light intensity to minimize the scatter. We can also modify the dimensions of the CAD model. We've got a database at this point of overpolymerization caused and experienced at different feature sizes, energies, and slurries. So we can modify the CAD model in advance of printing to account for that overpolymerization. And if it changes a little bit with individual features, it's the iterative process of additive manufacturing. But because we can iterate several times on the same build plate, it's very easy to iterate through green models. We can put 3 different sizes on one build plate and figure out exactly what overpolymerization each feature is experiencing and find it out all when one print finishes instead of having to wait for the part to go through the entire sintering process. And you could probably predict my last point of this is, again, we can orient the parts to protect those critical features. Knowing in advance whether it's a fitting feature or an exact tolerance, we can change how the part is sitting on the build plate to change the light density around a given feature. We keep talking about print orientation because it's really interesting and it's one of the easiest tools that we have to change what final part looks like. On the lithos printer, the part is hanging upside down, and the vat has only enough slurry for a single layer, every layer. It's very efficient in terms of slurry use, and it actually allows the slurry to drain out of open features because they're hanging upside down. But it also means that we're fighting gravity with every layer because of the weight of the part. And any feature that closes up before the print is finished traps any remaining slurry inside it facing the build plate. It also means that the face of the part that's attached to the build plate needs to be large and flat, or we have to add some supports to keep it attached to the build plate. Overhangs have to be able to support themselves against gravity, or we have to add supports to keep them from flapping around. On the Prodways printer, the light's coming from the other direction. The part descends into the vat as the layer build up from the positive Z direction. So we aren't fighting gravity, but the part is filling up with slurry. Any feature with a partially or entirely closed cavity is going to come off the printer completely full of slurry. It increases our slurry usage and increases the time required to clean parts. Additionally, the part has to be connected to the build plate well enough that it doesn't float up and away during the printing process or get knocked over by the slurry in the blade moving across during each recoat at the end of the layer. So with these kind of opposite methodologies, We can choose the printer model and the print orientation depending on the part itself. So minimizing the supported faces is pretty easy for if we know in advance which are the critical features. And we can choose where the supports are and how it's sitting on the build plate to do that. We can also leverage those drain holes that I talked about earlier to allow collected slurry to drain either during the printing process or during cleaning, so we can flow more solvent through, get all of that excess slurry out, and end up with better tolerances and cleaner internal features. Sometimes that print orientation might mean the print takes a little bit longer because it has to be printed in a vertical instead of horizontal orientation. But because the cleaning and thermal processing, as well as the post-processing, cleaning up any residual from supports, are all simplified, the final part actually ends up being less expensive and much higher quality. Overall, the things I'd like you to remember as you're designing and working with parts for ceramic additive manufacturing is that the wall thickness is a material limitation. We have a maximum wall thickness based on the raw slurry. So adding kind of lightweighting features, making sure that wall thickness is consistent all the way across the part will help us get a successful part out. Use fillets as large and as often as possible, and add drain holes anywhere that you can so that features are better cleaned and the internal features are more true to the design. We also have to take into account that shrinkage and make sure that if we are aligning features to the pixel grid, the scaled part is what actually aligns. As we're printing, spend a lot of time looking at critical features and faces so that we can orient well on the build plate, both to maximize efficiency and protect the critical features. That also allows us to minimize the number of supports required and consider what overhangs and other features require the supports, minimize those where we can. We also have to look at the light scattering and the light density in the critical areas. That's more of a CAD model and a design, but also impacts the print orientation as we're going through it. I think that's all I've got from a technical perspective.
Okay, thanks, Adriana.
Back.
Thank you very much. Next slide. So obviously, folks, you can tell that this has been many thousands of hours of R&D on Adva Cera's behalf. So we've really unlocked a lot of key knowledge of how additive manufacturing for ceramics works. Now, I'd like to bring in my esteemed colleague, Dustin Williams, who runs business development. This is actually the second time I've had the opportunity and privilege to work with Dustin, and he's done a great job with both companies. So he wanted to spend a little time piecing this together and talking more about collaboration and opportunities. Dustin, take it away.
Yeah, appreciate that. Thanks, Hugh. And great job, Adriana. You know, she was one of the first employees at Adva Cera, formerly Synaptic. So she's really kind of paved the path for this development of our materials, using the technology that we have. So she does a great job working with customers and understanding the application and how we could potentially provide solutions for some of those applications. But why don't we move into what kind of materials, right? Like what are we printing exactly, and how can they be used? So here's a list of the materials that we are working with currently. Let's go ahead and start with alumina. You know, it's really the backbone of technical ceramics. And, you know, when this technology, DLP technology, was first invented 12, 14 years ago, this was the first material that it was developed for. So it's a widely used ceramic. It has a great combination of hardness, thermal stability, and corrosion and wear resistance. So there's many applications that can be utilized with alumina or aluminum oxide. It prints really well, and it can be processed, you know, in an oxygen environment. So that's always helpful in our post-processing of producing these parts. Kind of next on the list, and also next from a volume standpoint of what we produce, is zirconia. You know, zirconia is a very tough material. It can be referred to as ceramic steel almost. It's you know, got some great hardness, very high fracture toughness and resistant to crack propagation. It's a great choice for structural components, more applications where there's probably some more mechanical reliability is critical. And interfaces, with other materials, metals, really well. There's some nuances to printing zirconia as compared to alumina, but our team, works with it quite frequently. And we're going to get into a little bit more of applications for each of these materials in the next couple of slides. Another one that I wanted to mention, and perhaps maybe not as popular or in need for the America Makes audience, but I do want to mention it, is a bioceramic hydroxyapatite. So for those of you who don't know, hydroxyapatite is a form of calcium phosphate. It's the mineral that is the structural component of our bones. So it obviously is extremely biocompatible. It supports bone growth, bone healing, providing that scaffold for the biological component, the cellular component of bone healing. So for this audience, could have a potential for like in-field warfighter medical applications. So it's a very unique material for us. And we've got some great examples if there's any interest into this kind of unique material. The other two that are a little more technical than perhaps the oxide ceramics, silicon nitride and aluminum nitride. I want to start with silicon nitride. Since we're using light to produce these additively manufactured components, silicon nitride's a little bit on the darker side. So it does, have some unique characteristics in printing that ceramic. It is a material that could use some more development. And honestly, it could use an application-specific development process. So, it's a very tough ceramic as well, great for thermal shock resistance. If there are some applications where perhaps you have a project that could utilize silicon nitride, while we are developing the manufacturing process for this material, it would really help to kind of connect and understand, what are the requirements for your projects that a silicon nitride could be utilized for. Lastly, I do want to talk about aluminum nitride. We've been working on our manufacturing process for aluminum nitride for quite some time, and recently have seen some great results. It prints really well, but since it is a nitride, we do have to control that post-processing environment, which is also extreme, and from a temperature standpoint, quite strictly. The advantages of aluminum nitride are its high thermal conductivity. It's got great electrical insulation, but I think the strongest characteristic of aluminum nitride is that low coefficient of thermal expansion. When you compare that with, say, like an alumina, it does have that advantage of it doesn't expand nearly as much as an oxide ceramic. So it's an attractive material for those extreme environments that see some high heat, but still need to perform from a dimensional or structural standpoint. Why don't we go ahead and move to the next slide? We can kind of start getting into some specific applications for some of these materials. So kind of starting with aerospace and defense, the audience within America Makes, this is a high vertical for most of the members within the organization, as well as ourselves, right? Some of our biggest market segments, aerospace, defense, semicon manufacturing, a lot of industrial applications, filtration applications. But specifically talking about, aerospace and defense, weight is always going to be a consideration. So with our ability to create these complex geometries and hollow out areas or lattice areas to save some weight, save some density of parts, of course, we have that advantage. And of course, we're talking about in extreme environments, and these materials can withstand, a lot of those environments. Another thing, Hugh kind of touched on this. Manufacturing ceramics is not easy from a traditional standpoint, and therefore it's also costly. So there are some applications, perhaps where there's some low volume needed. And the only other way to maybe make a design is a complex tool, which we all know are very expensive. So we do have some advantages there of potentially reducing costs for some of these complex designs. And that customization that just perhaps isn't possible with traditional manufacturing as well. Can we go to the next slide and talk a little bit more about some specific applications? So you can see these verticals here, a lot of market segments that we are producing parts for currently today. Most of the projects that we are producing parts for are, under NDA protection, and we can't talk about a lot of the specific designs. But I did want to at least touch base on a broad standpoint of what are these parts used for. So let's just kind of start with alumina. We do a lot of internal features for the alumina components, high voltage insulators, RF microwave switching or filter components, corrosion resistant manifolds or gas diffusion nozzles, radomes, some other dielectric structures, fuel cell components, filtration, both in extreme caustic environments and also high temperature filtration environments. And we can also tailor porosity from a macro and micro standpoint. So whether that's design or perhaps permittivity of the material as well. Zirconia is also, has some great applications, aerospace and defense, valve seats, sealing rings, pump components, plungers, liners, any areas that you're going to see high wear in surfaces, or perhaps something that has a high wear environment, but with that complex or radiused feature of a design that could be difficult for those traditional ceramic manufacturers. And then finally, again, want to go back to aluminum nitride because of that excellent thermal property and thermal performance of aluminum nitride, heat exchangers, right? We get that inquiry all the time. So lots of baffles, lots of internal channeling for aluminum nitride heat exchangers or heat sinks and complex cooling systems. Can we go to the next slide, please? So just, as some of these have kind of already been commented on, I wanted to show this as an example. This is an exhaust nozzle for, a drone application, something that was a variation of a prototype for a project that we were involved in. I mean, you can kind of just give you an idea of the complexities of the geometric designs that we can produce on our platforms. And next slide, please. So, of course, I do have to just comment real quick on kind of business side of things and how we handle projects as they come in. The additive manufacturing platforms that we utilize for ceramic production, they're taking advantage of lessons learned from other materials, metals, some polymer technology. It is an iterative process, as Adriana referred to in her section. So we have kind of set up our service portfolio to handle that in an iterative process where we like to prototype for our customers. It helps us establish process for each design that comes in. And it also helps our customers test these designs. And most of the time it needs some optimization, whether it's a feature or perhaps an area of the part that needs some additional latticing or wall thickness reduction. But we are really set up, as Hugh pointed to earlier, for serial production. We do have multiple printers, multiple furnaces for large capacity runs. And that really is the goal here, is to do series production. We also have a very, very robust quality management system, inspection capabilities. So our team is set up to do first article documentation for those serial production runs. That process does take time and volume in order to prove out some of those processes, but we do have those capabilities. And lastly, I am currently out in Munich, Germany. As Hugh mentioned earlier, I'm attending the Ceramtech conference that's held every other year. It's exciting to be out here and kind of talk about where ceramic additive has come in the last 10 years, 10, 12 years, and where it's going in the future. I think we're kind of on the precipice, right, of a lot of market adoption. Aerospace, defense, semiconductor, manufacturing equipment, and lastly, investment casting. We are just in the early stages of starting to work with a new material, silica, that could be used for investment casting cores. So think about lightweighting turbine blades in that investment casting process or casting core process. I really see a lot of industries starting to take advantage of this technology, and we are every day fielding calls from additional industries or additional partners in industries we are already working in. And you can kind of see what the projection is for ceramic AM. I mean, the marketplace is really set to explode, and they're projected to reach 2.5 billion by 2034. So what is going to drive this? I think it's additional materials. We work very closely with our printer manufacturer partners and material providers. So as the technology matures and new technologies are introduced that can be utilized for ceramic printing, the materials are also going to mature and grow with that. Another thing that I've seen more recently in the last 12 months is that digital manufacturing or digital modeling. As Adriana pointed out, there are some design-specific parameters for ceramic additive, and there's going to be more and more digital modeling that follows that. So the engineers that are on the front lines designing these parts are utilizing the parameters and rules that are kind of being set for ceramic additive to produce the most efficient designs. And then lastly, is standard development. We are, as Hugh mentioned, working with some of those organizations that are beginning to address standard development for ceramic additive. It's going to be needed, especially for some of these industries that have some strict regulations, as well as those industries that are going to adopt this for mass production. So we want to play a role in that. We are very early in this stage, and we want to be known for our part in establishing some of those standards. So I think a great way to close is, how do you get involved, or how can we help provide solutions? There's been several conversations where an engineer will come up at a trade show and say, "I didn't even know you could print ceramic. You know what? Like, this could really help us out with this problem we haven't had a solution for months." So we are actively looking for project calls within the American Makes organization. You can reach out through that, or you can just reach out to us directly. You can see our website information here. We do have a contact form on our website, or a general inbox there at info@advacera.com. That is a QR code that will take you directly to our website, where you can find some additional information there. And then final comment, ceramics are materials too. When we first joined the American Makes organization last year, it's been great. We attended our first member meeting last year, talking a lot about metal additive. And I think it's our role, it's our duty to say, ceramics could really play a role in this industry, multiple industries, and perhaps provide a solution for an issue on one of your projects. So with that, I do want to leave a little bit of time for questions. So you can see our contact information here on this slide, and want to open it up if there are any questions after this presentation.
Thank you, everybody. Yeah, so we've got a question about the slides in the chat. We will be sharing the slides with the attendees here. So if anybody has any questions for the team on the phone, feel free to raise your hand, pop off mute, kind of just shout it out, put it in the chat, whatever works best, whatever makes you feel the most comfortable. Feel free to open up some dialogue.
We must have addressed, all of those questions.
Stuck the landing again.
There we go.
Here we have a question. What is the largest part possible?
Yeah, we get that question a lot. I'll probably let Adriana answer that from a detailed standpoint. There's always some gray area of largest part, because printing is kind of the easy part with ceramics. It's that post processing, it's the debinding, sintering that it is always going to be the deciding factor. So I guess to answer that question from a dimensional standpoint, Adriana, if you want to take that, it's going to be, say, depends, right? That's always going to be a good answer.
Yeah, so we are limited by wall thickness, sure, but the largest kind of external dimensions of the part that are possible with the printers that we have is 264 by 328 millimeters in the green state. So depending on whether you're looking for an alumina part or an aluminum nitride part or silica part, those are going to be have slightly different shrinkages. So take 20% off of that, and I admit I can't do that math in my head, but the largest build plate that we have is on the Broadways with that modular build plate. So 264 by 328 by 350 times minus about 20%, you can average. Assuming that your wall thickness is within spec, and that's just your bounding box.
Yeah, I see that next question is a great one. What's the thinnest wall thickness that we can go? That is going to be also feature dependent. I get asked that question and I always answer it wrong, because the engineers say, no, Dustin, that's going to be too challenging. I'm going to address that kind of from a general feature aspect. So channels, right? People always ask, like, what's the thinnest channel or smallest diameter channel you can create? Length of that channel, as Adriana pointed out to earlier, is going to be the deciding factor of that. We have created structures, 200 microns or less, but you got to think about the surrounding structure. So that is going to be very design dependent. We have that resolution of 40 and 31 microns between the two printers. That doesn't necessarily mean we can print a 40 micron wall on a part. But so it's going to be very design dependent, and the best is just submit your design or submit your idea for a design to us, and we can chat through that. Did you have anything to add?
Yeah, if you don't mind. If we're working with a part that is a consistent thin wall, we've got lattice cubes that have 150 micron struts, and the whole part is about 1 centimeter across. But because all of the walls are consistently thin, we can do 150 micron walls with, I think they're about 200 micron wide channels, because the whole thing is very thin and debinds really evenly. But if you wanted to take a 4 millimeter wall base of the part and add a 0.5 millimeter thin wall on top of that, you would have some difficulties unless it was dramatically transferred at the transition from that thick to that thin section. So that's where the feature dependence come in, is we can make the really small stuff, but the rest of the part has to be able to accommodate it during the processing. Does that help with that question?
Yeah, I think that was some great addition. We've got one other question. I think it's related to what kind of open chamber, what's the max size of open chamber we can do? And that's also going to be a depends answer, because we can always support open chambers, right? It's, can we get in there after printing to remove those supports and then process? So it's going to kind of depend on an access. Each material does have its specifications for open radii without supports, or T overhangs, H-type overhangs, and each material has its own kind of unique green state handling characteristics. So that's kind of a complicated question. Again, it just, why don't you reach out and let's talk about that application and which material you're looking for, so we can best answer your question.
All right, we've got a live question from Brandon Cox.
Hey guys, can you hear me?
Yes.
Hey, so I've been working in standards development for AIM Ceramics for a couple years, a little more than that actually, but we have some standards that are in the works. Our first standard was published recently through ISO ASTM. My question is, are there specific things that you guys are looking for, you see a need for when it comes to standardization? Just to do like a quick summary, right now there's been a big focus on like feedstock standard development when it comes to characterization of feedstock materials, more on the VPP side, like DLP related. Design also, there is an upcoming standard that will be drafted soon that NIST is working on that's focusing on imperfections. So like common defects that cause, material failure, that sort of thing. Let's see, a novel test method coming out by University of Leoben. They've done a lot of studies on that, where they're doing they've developed a new way to test flexural strength of AM ceramics rather than like a 3 or 4 point bin test. So sort of beyond those, do you guys see anything that you need on your end that would be useful when it comes to standardization?
I think those are all going to be really helpful, and I'm very much looking forward to them. And I think some of the other things, and this kind of falls in with that creator that we were talking about with NIST earlier, is testing methodology standards, because there are some different ways that the different properties can be measured: the curing depth, the viscosity, and green strength. So having standard methodology so that green data is comparable across manufacturers and slurry manufacturers and service bureaus, I think that's going to be really helpful as well.
Yeah. Thanks for sharing that information, Brandon. That's really helpful.
Yeah. Okay. Good to know, because I can get things moving on that end. Usually one of the hurdles is having like a project leader to own the standard development. So more to come.
Can we set up some time to talk with you offline?
Sure, definitely. Anytime.
Okay, great.
Yeah, I do owe you a response, Brandon. Thank you for your note you sent to me earlier in this week or last week. I've been on the road for a couple of weeks, so when I get back, Hugh and I will sit down and we'll definitely schedule some time with you.
He pesters the engineers too much when he's here, so we move him out around the country and the world.
If I was in Germany, I wouldn't care too much about responding to emails either, probably.
All right. I believe we had a couple more in the chat.
We did. So there is a question about max wall thickness. There's a lot of options about reducing wall thickness. So it's going to depend on what are the critical features, what is the performance of the part, where are the stresses that are going to be applied to that part. So we have a lot of options to address wall thickness, and if there's a current design that would exceed, the limitations of the material, again, I just iterate, it's going to depend on a lot of things. So if you could reach out, send either myself or Adriana or Hugh an email, book some time with you and talk about your design and where we could offer some suggestions to reduce wall thickness. And then one from Jessica talking about silicon nitride and design guide for silicon nitride. Yes, that is on our roadmap. As you mentioned in your question, the light absorption of that ceramic poses some unique challenges. Of course, that is our goal, to have design guides. We've got some very good ideas of what that would look like. So if if, again, there's a specific application for silicon nitride or a project that you're working on, that would help to direct some of those suggestions or design guides, if you'd like to book some time to chat about it. And then post-processing capabilities at Adva Cera. I guess Hugh or Adriana, do you want to talk a little bit? You might have a little bit better response to some of that.
Yeah, I can jump in here. So for the post-processing, we have a variety of technologies, including solvent flow, so pumping solvent through, using ultrasonic cleaning, ultrasonic knives, centrifuging to clean the parts out after cleaning. And depending on the part, how thin the walls are, how fragile the part is, how big the channels are, we use a variety and a combination of air, sonication, centrifuge, and solvent flow to get all the parts as clean as possible. But there's no one-size-fits-all answer because it depends. It depends on the part. It depends on the length of the channels, depends on the drain holes. But we do have, for each of these slurries, we've got some really well dialed in processes for getting them cleaned out.
Some of your baseline work with some of your customers, do you have like cleanliness specifications that you develop with the team?
I don't know that we have part specific specifications at the moment, but as we're developing the processes for the different product lines for customers, there is a standard and there are specific inspection criteria that each of the parts have to match. So I guess that would be the specification. Yeah.
Okay.
Are you specifically asking clean room facilities?
No, mainly for complex shapes like lattices, because I think the presentation kind of showed that we know that it's hard to get all of that slurry excavated out. So then there's challenges for A, dimensionality, and B, performance of internal channels. So curious if you guys had that experience in developing.
Yeah, and
maybe
we've got
cleaning guideline is not the right word, but post-process guidelines.
Cleaning guidelines is something that we would refer to it as internally. Yeah, and we've got a couple different ways we can check. So green volume of the part is one way. Once it has been determined what it takes to actually get a part clean, then using some green volume gas picnometry to make sure that parts are staying clean at some AQL level within a build or a process is one thing that we have looked into and are developing our own internal standards around.
Great, thank you.
Then the last one I see in the chat. I guess I'll address your last question, Jessica. Yes, we do have in-house furnace debinding and sintering capabilities. So definitely can handle that in-house. And then the last question regarding, again, wall thickness, the 10 millimeter max wall thickness before or after sintering. That would be a sintered dimension. And again, we're going to be feature and design dependent. So what our team likes to do is kind of put a radius or a sphere into the model and see, where is that max wall thickness, because we do have to think about diffusion of that gas and as close to consistent wall thickness across the whole part as possible. So the shrinkage rates through thermal processing are kind of matching from left to right, top to bottom, however you're looking at the part.
Yep. And just to add on to that, it is also material dependent. So one slurry, one ceramic may have that 10 millimeter watt thickness, where a slurry with a different photoresin system is going to debind differently. The debind rates and products are going to be a little bit different. So that one will have a different wall thickness based on what material our final product is.
Yeah, all fantastic questions. We really appreciate the engagement and the time that you guys have taken out of your day today.
Yeah, absolutely. So Thank you, everybody, for joining us and staying with us for Adva Cera's presentation and all of the questions there at the end. We appreciate the engagement, as I believe Dustin said. So if anybody has any questions, feel free to reach out to the Adva Cera team. And with that, I want to say thank you and have a good rest of your week. We'll see
Thank you,
everybody at
everybody.
Rapid.
Take
Thank
care.
you all.
Thank you.